Next up, we have Mr. Ray Beach from NASA's Glenn Research Center. Ray will be speaking on NASA applications for flywheels.
Thank you. I guess in looking at the last presentation in ours here today, I think what we have is more of a indication of NASA's desire and looking at flywheels and how we would apply them in space, and in particular where carbon nanotube fibers may be critical to us and important to us in the future, especially as we look at the different applications associated with the return to the moon and going on to Mars and the exploration initiative. And the title was a spiffy way just to say that we're looking at space-based energy storage, but as you'll see in a little bit, it's not just energy storage we're interested in. The flywheel actually impacts a number of different systems on board the spacecraft, and that in particular is why we've spent the time we have in the development area for flywheels. Now, most of our effort to date has been concentrated on getting a flywheel system developed and demonstrated in the lab sufficient to allow us to progress on forward to a flight application. Where we stand today when we talk about flywheel systems is we're talking about a unit, a module that contains a fiber composite rotor. Today, Richard Thompson from the University of Texas is going to follow me talking, so we've split the time between us because the folks at the University of Texas have been involved in all of our rotor development activity, and he's going to talk about both some of the activities they've done for us as well as other activities that they have supporting flywheel rotor development. And you can see on the bottom over here on the right, our university rotor development partner is the University of Texas Center for Electromechanics. We also, in all cases, are suspending the rotor on magnetic bearings, since we are going after a device that will give us very long term operation in space. And in some cases, in low Earth orbit, we're talking about many hundred and some thousand cycles to go for 15 years. Typically, a battery system today on a spacecraft goes for about 5 years in low Earth orbit, and then we either have to lose the satellite or, and in the case of the space station, we actually replace the batteries every 5 years. So if we have a 15-year station, we have to do 3 sets of batteries over the life of the station. Getting it up and suspended on magnetic bearings is key to us because that's a way to get around the problems we would have if we were suspending it on ball bearings. Also involved, of course, is a motor generator, which is our way of getting the energy in and out because we have to interface with a DC bus on the space station. I don't have any electronics showing up here, but the electronics would also be in front of the motor generator. We've been involved in the development of the motor generator activities back at NASA Glenn. And the magnetic bearing work, I didn't mention our partner is just up the road is Texas A&M. So they also have been involved in all of our magnetic bearing suspension work. That's both for the flywheel as well as gas turbine engine, hot magnetic bearings for gas turbine engines. We also have been working with the folks at the University of Toledo that have worked with us on the touchdown bearing, which is just a way for us to get up through our launch loads, and the development of the rest of the system in the housing mass and all that has to be wrapped around it so we can put it all together, put it on a spacecraft and spin it up so we have that energy to deploy the satellite when it reaches orbit. Now, why we are really interested in flywheels goes way beyond just energy storage. And what I tried to do is indicate the steps that we see as future steps that we're going to take if we're going to really utilize the full capability of what a flywheel provides to us for a spacecraft. In particular, the top part of that chart, if you can read it up there, is modular systems, and that just indicates that in all cases our components in the electronic world have all been developed to be modular and support the flywheel activity in the area of the magnetic bearing suspension and the interface to the spacecraft bus. At the moment, we're concentrating on the IPAC system, which is integrated power and attitude control, and that would, in essence, replace the batteries that we currently use on orbit, as well as the momentum system. So we want to combine those two and put them together. And our benefits to be achieved in the flywheel area are because of the long life and the ability to still go deep on depth of discharge, and simultaneously combine that with the momentum system or the attitude control system and provide both those two systems now into a common single system. Beyond that, what we're looking at is providing independent outputs on the flywheel, which we can do because all we have to do is put a motor generator specific to that application, so we can go very high voltage outputs and still have another unit on board that allows us to interface with the low voltage spacecraft bus and provide that high voltage output to the propulsion system, electric propulsion system, or a electrodynamic tether would be an example of how we would combine then to provide those functions to that particular load, eliminating any kind of power processing or separate bus that would have to be on the spacecraft. And then eventually what we're looking at is the applications, especially for most of NASA's satellites and most commercial satellites, involve a number of flywheels that are placed in a tetrahedron to give you that ability to have 3-axis control plus your energy storage. In doing that, you wind up with a very natural structural element, the tetrahedron. So we're looking at how do we take advantage of that rather than build the flywheels and place them on the spacecraft. We want to build the spacecraft and the flywheels as an integral unit, and we provide that structural capability as a part of the flywheel element itself, multi-flywheel element in the case of the attitude control function. So in the end, we wind up with the multifunctional structure providing energy storage, attitude control, the high voltage capability for the electric thrusters, and the structure itself. We have primarily focused our development activities on that first goal of combining the attitude control and the power system together. And what I'm showing here in the case of the picture is a couple of units that have been run back at the Glenn Research Center. They demonstrated 2-axis control plus power. So what's shown in the photograph, a little hard to see, but there's 2 units located on an air-bearing table. We can position that table any way we want, take the energy in and out at any time, go through transition periods from eclipse into insolation and back again. So we're providing all of the bus control at the same time that we're capable of maneuvering and steering the platform itself. The big issue there is the power system has to react with a bandwidth of about 1 kilohertz, and in the case of the momentum system, you're talking a few hertz. So the primary goal and effort was to demonstrate that we could completely reject any kind of a power system disturbance from ever getting through and disturbing the attitude control system. Now, we're kind of lucky because we do fly flywheels already on spacecraft, so we've got a fairly significant community of people that are open to the idea of high-speed energy storage wheels. And the overall schematic shows, in essence, that we have to provide that bus control, the attitude control, and, of course, the primary power is coming from the solar array, and then we're providing the bus control during the eclipse period from the flywheels themselves and have completely replaced the batteries. This is sort of where we've been. We've concentrated a good deal of our activity in the lab area. We have had the opportunity to proceed on forward to flight designs, which is shown up in the top portion in the green. The only thing I wanted to indicate here was that we've had a series of units that have been built and tested at Glenn. We run them every day. We run them up to 60,000 RPM. We have managed to demonstrate and achieve all of our performance goals, which are indicated both with respect to the combined system, the IPAC combined system capability, that we can reject any of those power disturbances from the spacecraft control bus, attitude control bus. And in conjunction with the folks down at the University of Texas, we have built we have designed several units and built hardware for several units that we're hoping to take to flight status in the very near future. And those 2 points are shown in the green area, one being at 3,000 watt-hour unit that was built to go on the space station and demonstrate flywheel technology just as an energy storage only device on station. and the other unit a little bit off to the side there, which was designed to be utilized either on station or for a commercial satellite. And again, in both cases, we've achieved fairly significant improvements in the specific energy. And just as an example, I know that the battery folk provide wonderful high specific energy numbers, but for us, the issues always came down to how do you take that battery cell, configure it into a battery, and then design the power system to get the life that we need. And we literally designed the entire spacecraft around the battery system. The entire spacecraft power is designed around the battery system. So we baby the battery to get the life that we need. What we're after with a flywheel is the ability to not have to design our power system around the battery, but design it for a particular power application. If we want to hit it with a big pulse, we don't want to have to add extra capability. We'll just have that capability and be able to do it without having a life impact. So it's those comparisons at the system level which are the primary driver that keeps us going in the flywheel area. So if you look at it, say the 35 watt-hour per kilogram number, and you compare it to a lithium nickel hydrogen battery, it looks to be a low number, but if you look at what we have to do to put that battery on a spacecraft, you start off with 120 watt-hours per kilogram at the cell level, and we wind up with about 7 watt-hours per kilogram at the system level. So when we come through with something at the 35 or 30 watt-hour per kilogram level, we're talking many times the capability that we get currently in our systems. Now this, our progress, which we've been very happy with, has led us to begin to look at what would it mean if we were to project ourselves forward, looking again at the return to the moon and potentially Mars surface power operations. And what we were asked to do was work in conjunction with a study team to look at whether or not we could have a solar option instead of the nuclear option. I think a lot of folks know we had for a while been putting a significant amount of money into developing a nuclear power source to be used on the moon and on Mars. So this was strictly a study that was geared, it was a parametric study geared to look to see whether or not we actually could open up the door to a solar option. Now the issues associated with a solar option, of course, on the moon is we have to provide that power for roughly a 14.7 day period of time when we no longer have the sun and we are in the eclipse period. So in looking at that, what we did was look at both a fuel cell-based system and a flywheel-based system. Now the big issue in terms of being able to provide that is we have to be able to put everything we need on a single lander that goes to the moon and can deploy and give us the capability, and all we have to do is run a cable between it and the HAB and lab portions of the lunar base, and we'd have our capability. So we were very constrained by the mass requirements associated with the lander itself. So what we did was, it was strictly a parametric study. We looked at what some of the potential was for carbon nanotube fibers, which when you look at them sound a bit like unobtainium, but nonetheless we took the best data we saw out there, and we then looked at our current designs and what modifications we'd have to make to our designs in order to develop a concept. And it's not completely a concept design because we did not go through a whole design process for it, but just looked at projecting forward from what we knew we had learned from our current systems. So in essence, we took data based on superconducting magnetic bearings that we obtained from the Boeing company. We also worked with the Boeing company with respect to what they saw as the projected numbers for the carbon nanotube fibers. And then we looked at the rest of the system and how we would put it on the lander, package it on the lander, and the kind of shielding requirements we would need and so on. This is basically an indication of what that would look like. The bottom portion, of course, is the lander and the fuel tanks associated with the lander, and the top part is where the flywheels would be mounted, and of course it shows a deployable solar array in the artist rendition. The module shown off the side is actually a module that we're building to support the space station effort. So it was strictly just a graphic to indicate roughly the size that we saw for the unit. And we also looked at taking those same units and being able to put them into a rover. And the feature that came out of that, which we were really kind of excited about and still are, is that we have a means, again, because we can put a very high-power generator along with a low-power generator that would provide the output to the rover, we can recharge it very quickly. So if we have some means electrically, we can pull the rover up and charge it up in a matter of minutes using a very high-power generator, and then go off and do your thing using the low-power output that would be required to drive the vehicle and provide the power for the vehicle. Some of the results of that study are shown in the table. There were 20 units total, and the overall system watt-hour per kilogram number came out to a whopping 1315. And we don't want to by any means say that we think we're going to be able to achieve that. That's only a number based on what the carbon nanotube fiber may provide to us in terms of its ultimate capability. However, I do want to stress, and I think Richard Thompson will talk a little bit more about rotor development, that's a very, very derated figure. So we are not running this thing anywhere near its maximum capability. So to get life and to have a safe system, since we have no containment, it has to be heavily derated to get to the operation in space. The operating speed, again, 83,000 to 250,000 RPM. And again, if you look at that number and you look at how we're going to get there, we're hoping the superconducting magnetic bearing is going to give us that path to get to very high speeds. Our current magnetic bearing systems are all actively controlled. We could not take those to these kinds of speeds, so we need a totally passive system that gets to its suspension through physics alone, and at the moment not through an active control system. We are very bandwidth limited if we were to go anywhere near those kind of operating speeds with the active control. In conclusion, the only thing I can add here is that if we had this kind of capability, have no doubt that we would exploit this technology, and that it opens the door for us to be able to go non-nuclear on the moon and to go and eliminate some of the problems we're going to have if we implement a fuel cell system. And most of those problems associated with the fuel cell system come in terms of the length of time that we can get out of the fuel cell stack, as well as the leak and loss of your reactants over a period of time, and what that costs us in terms of resupply to keep the whole system working. So in the end, it stacks up very favorably for flywheels. And based on our study results, we probably could go from a 25 kilowatt capability on a lander to a full 50 kilowatt capability. And that absolutely gives us the full capability that we currently are projecting for lunar operations. I guess in conclusion, the one thing I wanted to mention is we are proceeding forward with our development activities as they are associated with getting flywheels into space and demonstrating them, which is a big hurdle. We always have a catch-22. If you haven't flown, nobody really wants to fly it. So one of our goals in the very near future is to get flywheels up into space, improve their capability, and get them out into application. That's near term. And then far term, what we're looking at is combining with the University Consortium and Northrop Grumman as well as Boeing to put together a national capability, meaning distributed amongst the folks with the institutional capability like CEM, to foster the development and demonstration of high-speed flywheels like what we talked about here for a lunar application as we progress on in time and those materials fiber capability becomes available.
Thanks for a fascinating talk. We have time for questions. Go ahead.
toward levitating. Is it a smart flywheel that would use the levitation to have magnetic forces to generate electricity, and that can generate power also?
I guess I'm not really sure what you mean by smart. You mean an all-passive system?
Yeah, all-passive system, and the simple magnetism converting into electricity to generate power.
Okay. With respect to the suspension system, I think the answer would be yes. We see the superconducting magnetic bearing, which is an all-passive system, as having the advantage that we don't have to have any kind of redundancy. Currently, with the active magnetic system, we have redundant poles. We have to sense whether or not they're having difficulties or have failed, and then, of course, we have to have the redundancy associated with the controls, the power electronics, and the sensors associated with that, so it kind of ripples through. We can do that quite effectively, get our mass numbers for this near-term applications the way we should, but in terms of what we would do for a lunar application, I think we believe that the only way we're going to get there is through an all-passive superconducting system, both because it has no active capability. Its failure modes are very benign. We can spin it down as we lose that cryo-cooling capability. And it gives us a very, very low spin loss, and that's critical for the 14-day period. As it relates to the motor generator, almost all of our power needs tend to gravitate towards DC. It may be DC on the moon, high voltage DC, because we got to transport it a little ways, but it's going to probably be DC. So we do have to have some means of an active electronic control to take the AC off the generator and put it back out on the bus as DC. And of course, that's during discharge, and then in charge, take the DC off the solar array and turn it into AC to spin up the motor generator. Did I answer the question? Okay. 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 Thank you.
Thank you very much, Ray. The last speaker in this session is Richard Thompson, who is from the Center for Electromechanics at UT Austin. He's going to be speaking on kinetic energy storage and power generation.
I'm Richard Thompson, and we had two talks to do within 30 minutes. So in order to be on time, I think what I'm going to do is focus more in on the composite materials need for kinetic energy storage, for flywheel devices, and for power generation. I'll give a very brief overview of applications. Ray has talked about some of the space applications, but really focus in on what are the needs for these revolutionary improvements in composite material properties to bring this technology to the next level. Briefly go through this. Two categories. One is kinetic energy storage, flywheels. The other is using composite technology, but for permanent magnet generators. As we all know, stored energy goes with J omega squared. The specific energy, very important to space applications and mobile applications, is this ratio of the tangential stress divided by the density. Specific energy. Current composites, today's composites, have a benefit of about a factor of 6. For higher performance for flywheel energy storage devices, you need higher strength and higher modulus composites. Permanent magnet generators, the generator's power goes with proportional to d squared omega. D is the mean air gap diameter. Omega is the shaft speed. Higher performance, just very briefly, you can see down below you have some sort of a structural shaft. You have permanent magnet segments. Then you have a composite banding on the outside. That's the preload to hold the permanent magnets down on the shaft. To go to the higher diameter and higher shaft speed, again, you need higher strength composites and higher modulus. Application areas, Ray mentioned the dual mode use for space power, attitude control. At Center for Electromechanics, we build prototypes. We built prototypes for flywheels for advanced hybrid trains, transit buses. Defense is very interested in these high output megawatt permanent magnet generators. We've built those. We've built gigawatt machines using other technologies other than permanent magnets, but it also involves composites. Again, the need to go to higher strength, higher modulus. Electric power generation, advanced generators, these are mostly permanent magnet generators. They're megawatt class machines. They involve the composite overwrap. And of course, large-scale energy storage for power generation. This is just a concept for a very large-scale energy flywheel device. You're used to seeing kind of a flywheel with bearings on both ends. This is a different kind of a concept that may be a lower cost approach. The point in putting this together is what kind of weight is required in the rim to store, in this case, 8 gigajoules. That's the concept, just the example. It's about 65,000 pounds. When you start speaking in terms of $20 to $50 per pound, it's very expensive. So in order to get the boost you need in this technology to make it viable, it comes down to the price of the materials and then enhanced properties so that you can spin at higher shaft speeds. We currently have a sponsored activity with DoD. What they want to look at is for these permanent magnet, megawatt, and gigawatt class machines to go to the next level. So they've asked us to begin to look at a study, starting with a literature survey of who's doing what. What are the leading organizations that are developing these revolutionary fibers? Of course, the matrix has to be compatible with the fibers. They have different goals, different gates. Maturation issues, their first set of milestones is they want to see these organizations demonstrate the beneficial properties on an R&D scale. They want independent verification of properties. The second major milestone is out-of-lab processing. These materials must be in a form available for our sponsors for these kinetic devices and power generators. Initial findings, real quick, matrix, there's an incremental improvement. Looks like nanoclays are being used quite a lot. Literature shows it enhances structural and thermal properties in the neat resin. It's somewhat reduced when you put it into a carbon reinforced laminate because you have less of the resin involved. Initial findings on fiber, we looked at a Magellan's M5 fiber. That seems to be an incremental improvement. The real revolutionary improvement seems to be coming in the area of the basic science being done on carbon nanotubes. From the review of the literature, my take on it is embedded carbon nanotubes in thermosets has mixed results. There's been some issues with alignment, the interfacial shear stress between the carbon nanotube and the matrix, but both of these are continued to be worked. Emerging technologies that caught our attention is polymer wrapping, but in particular, in situ polymerization or co-polymerization. In this case, for in situ polymerization, our understanding is the carbon nanotube is aligned and embedded in a typical pan-type precursor, like an IM7 or T1000G. Two approaches. You can possibly, with the alignment of the carbon nanotube in the pan, you can generate a fibril, and then that can be conventionally impregnated with a B-stage epoxy and used for conventional filament winding. There's also a focus more on the carbon-carbon structure where you do the carbonization to advance the pan into a carbon matrix. Drexel University, a paper they have for the in situ polymerization, very encouraging results. They're indicating a twofold increase in strength and modulus over the pan fiber. They're actually doing some work with the Army on developing this for an application for missile cases. So what is the path to the future? Again, we're looking for the next enabling technology for structured composites. Has to offer these revolutionary improvements to really bolster this technology, benefit the kinetic devices and generator. Our next step in this funded activity is get a better understanding of the technologies and maturation issues, and then begin direct communications with the leading organizations. So that's where we are now. On time. Thank you.
We do have time for a question or two.
How much better than what you showed us do you have to be over here to achieve what we heard from the previous speaker?
Energy stored goes with speed squared. So if you can double the strength, you double the stored energy. So 50% increase for the military is a big improvement. They're looking for at least 50%, but anything over that is certainly welcomed.
You mentioned that stiffness was important. Would you comment on that, and what goes wrong if it's not stiff enough? And I'm also interested in what value for fiber strength was fed into the calculation in the previous paper, which gave, I think it was 1350 value.
Very insightful on the question. The reason you want the higher stiffness is for assembly reasons. It's much easier to take a stiff ring. A lot of what we do is by tapered press fit. So if you have a stiffer ring, the assembly is quite a bit easier. On the second part of the question, you mentioned 1350.
Well, I thought that was quoted. I thought that was quoted in the earlier paper, the previous paper.
Okay. On your talk, Ray, or on my talk?
Yeah. Sorry, I was expecting you to answer it, otherwise I'd have asked the question at the end of the previous talk.
Ray, can you answer it better? Or I don't quite understand the question because...
I think he was asking that 13, 15 watt-hour per kilogram number we had.
Oh, okay.
Yeah.
He's asking what was the assumption in terms of the strength of the fibers?
For the carbon nanotube assumption?
Yeah.
I don't know that one, right?
And again, it came out to be 17 times what
Okay.
T1000 was. That's what we had worked on.
Sorry, 17?
17,
Wow.
yeah.
The advertised tensile strength and modulus for carbon nanotubes theoretical is quite astounding. So whatever fraction of that we can get in practice would be a big, if it's a significant fraction but not the full amount, that's a big increase for this technology.
I agree entirely.
Thanks again.
Hi there. My name's Jimmy Glotfelty, and I'm the moderator for the second session here in the afternoon today. I wanted to just, first of all, invite our two speakers to come up. I see one of them, Dr. Luft, would you like to come up as well? The few things that I'd like to just put in a little bit of context here are when we talk about distributed energy as opposed to distributed generation, many folks who are far thinkers way down the road, like Dr. Smalley, are thinking about technologies that, like vehicles that are run on hydrogen fuel cells. And when you get to work, you plug them into the wall. And this is a two-way street. It's not a one-way street. You're not plugging in your car to get energy. You're plugging in your car to energize the grid. And as you do this in large numbers and large masses, you may have a concept for powering microgrids or small areas or buildings or so forth, just by the virtue of, instead of having your vehicle sitting there all day waiting for you to get in them and go home, they're working while you're working. We've got two great speakers. I think they'll shed a little bit more light on this. I will say that Dr. Jasna Tomic will be our first, and she has got a great background in this, and we look forward to your comments. Thanks.
Good afternoon. Well, thank you for that nice introduction. You've obviously looked a little bit at what I'm going to be talking about today. The title of the talk is Using Electric Vehicles for Grid-Connected Storage. But I'd like to put into context that as we've gone through the talks today, I think you will see in my talk mentioning a little bit of electric markets, storage of electricity, use of electricity for transportation, and addressing renewables. So I think this will hopefully tie in quite well to what we've seen today. Yes, let me just acknowledge I'm presenting this talk on behalf of myself and my friend and colleague Willett Kempton from University of Delaware. Energy-related problems. We're all aware that global climate change is increasing, and the recent risks indicate may be higher than previously realized and recognized. Second issue, peak oil production and demand outstripping supply. You know, that is, I think, what in a sense brought us here today. Third issue, we have renewable energy. It's plentiful, but limited by intermittent supply, wind, PV. So how can the vehicle and the electric grid system interact and address this? I will claim that there is a smart interaction between vehicle fleet, the grid, and intermittent renewables. It's a large, low-cost storage for renewables, and the vehicle-to-grid power can be used as a bridging technology to tie these things. How can electric vehicles benefit the grid? Number one, power of vehicle fleet is really a lot larger than the power of the current electric system. That's something I will show. Grid-connected vehicles can then provide profitable grid management, such as ancillary services today, and we've done some analysis to show that this is economically interesting, economically profitable, and technically feasible. A second, storage and backup for renewables. For example, wind power. Again, vehicles can be used as storage and backup for renewables. So those are the two things that I want to address today and show you how electric vehicles can benefit the grid. So let's look at the vehicle types. When I talk about electric vehicles, I'm really talking about electric drive vehicles, which means that it has onboard power electronics producing AC power. So it can be anything from a battery electric vehicle, whether a full function battery or a city car. The difference between the full function battery and a city car is simply in size of the battery that it has and the distances it can go. The fuel cell is also an electric drive vehicle. It can have either onboard hydrogen or be connected to a stationary reformer. And third, hybrid vehicles, which is a combination of internal combustion engine with a battery. So all of these three types are electric drive vehicles. Now this figure here shows us what are the current expectations of electric drive vehicles. On the, just see how this works. Oh, okay. Let's look at the battery vehicle. The current expectations are that the battery electric vehicle would charge off from the grid and then use that electricity for transportation. For the hybrid right here, again, the expectations are you'll get petroleum, convert it into gasoline, put it in to drive your hybrid using the internal combustion engine, or as the next speaker will address maybe more, plug it to the grid to get some electricity that way, but that's just one way. And use both those electricity and the petroleum for transportation. Third, if you have a fuel cell vehicle, you could get hydrogen from a variety of sources, I guess, and then use it for transportation. So those are our current expectations. Our proposal goes a step further. Why not go with the power of both ways? Charge from the grid, and then when you don't need your charge, discharge it back onto the grid. And why not even the hybrid go both ways, not even one way, as we're talking about these days very much. And the fuel cell vehicle, maybe it can charge from the grid, depending on the size of the battery that is on the fuel cell vehicle, mind you. It could be possible too, but it could definitely serve as a power source to discharge back to the grid. So in this way, you're using really these vehicles not only for transportation, but also as a power supply. Let me skip this one and go to the next one. So here on this chart, I want to compare the U.S. power grid system versus the electric drive vehicle fleet. So in the first column we have the U.S. power system. Mind you, this is based on utility generators, not on non-utility. So there's another about 200 gigawatts from non-utility generators. There's about 9,500 units in the power system, average unit power in 64,000 kilowatts. System power overall is 602 gigawatts, and again, that's of the utility system. There's another 200 or 300 gigawatts in non-utilities. In-use factor, 57%, and maybe even that's high. I've seen yesterday a figure saying 47%. That's how much they are used. Capital cost per kilowatt is over $1,000. And electricity cost, I guess, baseline average from 2 cents to 10 cents a kilowatt hour, and peak range from 5 to 80 cents per kilowatt hour. The vehicle fleet, in the US we have today around 200 million vehicles. If we converted the mechanical power of that vehicle into kilowatts, it's equivalent to 111 kilowatts, and that would be a number of 22,200 gigawatts, much larger. But this is mechanical power, so not really directly comparable. An interesting number, though, is vehicles are in use about 4% of the day, which means about 1 hour a day. You drive to work, you park, you drive back. So an average vehicle in the United States is parked 11 hours each day. So if we then look and consider that we have 25% of our current vehicle fleet as electric drive vehicle, that would be about 50 million vehicles. And if we say that each one has 15 kilowatt output, again, this is based on the power that the electric lines to your home or to your building office can take. We multiply that and we get a figure of 750 gigawatts of system power. So 50 million vehicles, 750 gigawatts versus the entire utility grid system, 602 gigawatts. Quite a remarkable figure, I would say. And electric vehicles can be in use more than 4% today because you can use them while they're parked to connect back to the grid and provide some power. Capital cost can range from $10 to $200 per kilowatt. Electricity cost from 10 cents to 50 cents per kilowatt hour, depending on the price of the battery, depending on your lifetime cycle, etc. This is how we imagine the vehicle-to-grid system. On the left-hand side, you have your generation, whether typical or atypical. These are wind-powered turbines. This is a nuclear feeding into the grid, then goes on with a distribution and transmission system to your home or to your office. And then you could have there your electric drive vehicle connected, or here at the office. You have the grid ISO, independent system operator, or grid operator in other regions, that via wireless communication sends signals to the vehicle owners, or probably in a system aggregator, to tell them when they need the power to be charged or discharged. What kind of uses for V2G power did we look at? Or what is the vehicle competing against when it's trying to sell power to the grid? So in principle, there's baseload power, peak power, ancillary services, and energy storage that we looked at that the vehicle could be used as. Baseload power really would have to compete against these big power generation stations, and economics shows that really the vehicle cannot compete at that level. You know, we cannot get a 2 cent per kilowatt hour out of electric drive vehicles. Peak power, I guess turbines are very often used for peak power. There are a couple of times a year, actually, that the peak power price of electricity is high enough to make it sensible to sell, but still that's not often enough. to sell peak power from these, but it depends. You know, again, you should look at it from market to market. Ancillary services is something more interesting, though, and that's what I will talk about today, mostly. What we use mostly for ancillary services are, this is grid management, basically, and I'll address it a little bit further on. A lot of hydropower is used for ancillary services. And then energy storage for allowing a greater penetration of renewable sources. So this part then of the talk, I want to address V2G power for grid management or ancillary services. And this is something that we don't really know enough about, or we did not know enough about when we had the regulated utilities. And with deregulation, this is something that has really become more transparent. You know, how these ancillary services operate, what they are, how they're priced, there's a competitive market for them, et cetera. And these are the two, or rather the one, regulation of power, regulation services, which I will specifically show you numbers for, and what the advantages of V2G power for regulation are. And the examples that we use, I'll show you two case studies, is using utility electric drive vehicle fleets for regulation services, cost and revenue calculations, and sample results of two actual fleet cases. So let's talk a little bit. Let me look at my time. Oh, the time is not running. I guess I have all the time in the world then. Ancillary services. Really, grid management maintains grid reliability. So the grid is not only about getting the electrons or the kilowatt hours from the generation to the load. There's all these other things. You have to maintain power quality. You have to maintain the frequency around 60 hertz. You have to have spinning reserves available to connect online. There's a suite of other things that are needed 24 hours around the clock. So basically, in principle, let's say simply put, you're balancing the supply and the demand because the electrons, once they start flowing, they have to go, and you're supporting transmission of electric power. Ancillary services requirements are somewhere between 5 to 10% of the system load. Two ancillary services that I'd like to talk about that I have looked at as interesting for vehicle-to-grid power. One is regulation, or regulation of power. And what is that? This is a definition. Online generation synchronized to the grid to keep frequency and voltage steady. Energy is increased or decreased instantly. That means within 2 or 3 minutes via automatic generation control. A second thing, I guess I should press here, are spinning reserves. This is additional generating capacity synchronized with the system to respond within 10 minutes in case of failure. They're called spinning reserves because what they actually used to do before is have the unit spinning at low speed so that it could quickly go online when needed. So these are fairly, especially the regulation, you need to respond within 2 to 3 minutes. Something an electric vehicle can do no problem, can respond within a second. And spinning reserves, and regulation, I should say, is used 24 hours around the clock. Spinning reserves as well, but I guess on average, maybe somebody from the utility knows better, but on average, spinning reserves are called around 20 times a year or 25 times a year. That's just a rule of thumb. The interesting part, however, is that the payment in today's market for ancillary services consists of two parts. One is you get paid for capacity price, or you pay dollars per megawatt per hour that you are connected and available to supply energy, whether or not you supply it. So just your availability to provide energy. And two, you get another energy price for actual megawatt of hours that you did provide. So there's two numbers there. And this is where this compares advantages of V2G for ancillary services. And the upper graph, it's kind of small, so you probably don't see it very well, but really shows how a typical plant, which is used today for ancillary services, which is hydro, has to fluctuate from its, let's see, I see better from here. This is its normal operating line, and then this would be regulation up, and this would be regulation down, that it has to fluctuate during a period to satisfy the calls that it's getting from the grid operator. A vehicle, however, can really remain around zero, right? It doesn't have to even be working. It's connected just by being plugged into the grid, and then it fluctuates around this. And this is a real power figure response from Brooks and al., a study that was sponsored by California Air Resources Board, when they actually tested an electric vehicle responding to the California ISO signal. So this is what they saw their vehicle doing in response to the signal. A couple of advantages are lower capital cost of generation and storage, rapid response in energy output, and smaller maintenance costs, perhaps too. I was looking at utility electric drive vehicle fleets for regulation. Why utility electric drive vehicle fleets? They exist today. There's actually a good number of utilities that have on the order of 200, 300 electric vehicles in their fleets, and this is to satisfy a federal requirement of having alternative fuel vehicles. Second, these vehicles are in a fleet. They have a predictable schedule. You know when they're used, when they're not used exactly. You can plan around that. And utilities are familiar with ancillary services. They know what that is. And we looked at two specific, there's about 5 different types of ancillary services, but regulation and spending reserves as of what we looked at, although today I would really present you the results of regulation only. It's a high-value energy market compatible with battery electric vehicles. And here are some of my cost and revenue equations. The top part is the revenue, and this is essentially what you get paid for capacity. The P contract is a contract price for regulation, or the dollars you get paid per kilowatt per hour that you remain online. The capital P is the power capacity of the vehicle, or very often power capacity really of the line that you're connected to. That turns out to be the limiting factor very often. T plug is the time your vehicle is plugged in. And then here is the cost of electricity. This is the cost of electricity, market selling price of electricity you use to charge up your battery, times the time, market selling price of electricity, the power you're providing, the time, duration, and then this RD to C factor, which is energy dispatch as proportion of contracted power. And we had to estimate this, given on some numbers that we found there, because this was not a figure any utility was able to give to us, but we came, we believe, to a fairly good estimate of that number. Essentially, nobody really knows to tell you exactly of the time that they're contracted. Let's say today they say they'll be 6 hours online, what % of that time they actually are used or not. And then the energy cost. What are the energy costs involved for supplying V2G power is, this is the cost electricity that you use to charge up your battery divided by the efficiency of grid to battery to grid, right? Some losses, plus the cost of degradation. So we did include the degradation costs occurring to the battery when you're using the battery for this power. And the degradation costs are essentially the cost of the battery, which is in dollars per kilowatt hour, and the lifetime energy throughput. 2 fleet cases. First fleet case is a New York station cards, and these are fleet cases that well, I guess I should say existed. I know they existed in 2003. New York Power, NYPA, New York Power Authority, had put in a program of purchasing 100 of these Think City vehicles. That was Ford Think, had these little two-seater electric battery vehicles, and they use them as station cars, which is allowing the owner to drive up to the commuter rail station with their electric vehicle, park it at the station, take the train to Manhattan, then come back in the evening and use the car again to go home. So while they were at the station, they were plugged in essentially the whole time. The second case is a California utility fleet with 252 Toyota RAV4s EVs. By the way, these have proven excellent. This utility still has these Toyota 4 RVs. So, am I running out of time? All right. So I'm using this fleet case New York Station car for regulation. I've included the upgrade cost for V2G. My power of line is about 6.2 kilowatts. The time the vehicle is plugged in is 23 hours. The cost of electricity coming out, this is what I charged on, and this is what comes out of my battery, is about $16 per kilowatt hour. And I use New York ISO regulation capacity price, which gives me $27.50 per megawatt per hour in 2003. And here are my figures. In year 2000, this total fleet power was 620 kilowatts. The revenue I would get for the entire year, if I was selling regulation, is $312,000 for the entire fleet. Cost $99,500, so my net profit is $212,000 for these 1,000 vehicles, which means that's how much they could get while they were parked. Let's look at the other quickly. Fleet case B. Again, for regulation services, I included the upgrade cost. The power here is a little bit higher, 15 kilowatts, because these are used for meter reading and such. So they're 17 hours they're parked, but the rest of the time they're used. 15 cents per kilowatt hour is my cost of electricity. The California ISO regulation capacity price for 2003 was for regulation up 19.5 and for regulation down about $20 per megawatt per hour. And here are the figures I get for this case. Again, for 2003, my total capacity, power capacity from this fleet was 3,780 kilowatts. I got revenue of $1 million, but it cost me $380,000. So the total profit was $660,000 for the entire year that you could get from selling regulation services. Not an insignificant number. In summary, you know what? Due to time, we can skip the summary. It just summarizes these two things. So EDVs are a promising source for grid power. V2Gs have high market value for regulation services and spinning reserves, and utility fleets can be early adopters of V2G. And just quickly want to show you a couple of. So which other vehicles do we have? Okay, this is definitely a fancy vehicle, a Venturi Fetish, but it's 58 kilowatt hours of lithium ion. It's V2G capable, V2G incorporated in it. It is a very speedy vehicle, 0 to 100 kilometers in 4.5 seconds. This is what it looks like. So that's a V2G capable vehicle. And then there's another series, EV Toyota Scions, which are expected to come out in about 18 months, a conversion done by a company in Southern California called AC Propulsion, who plan to get these Toyota Scions, convert them to EV with V2G capability. And just to show you the range, that's important for everybody, is 80 to 110 miles or 150 to 210 miles. These are the capacities of the batteries. Effect of EVs with V2G on grid infrastructure requirements. Some people say too many EVs are going to increase the load we need. Well, how much will they increase? And if we assume 100 million cars, each car goes 15,000 miles per year at 4.8 miles per kilowatt hour. We get 312 billion kilowatt hours per year at off-peak times. That's only 7% of 2020 total national load. With V2G, they can also provide a huge power resource, which is equivalent to 750 gigawatts of distributed generation, or 70% of 2020 national electric load. So not only do electric vehicles not present a serious load, they actually reduce grid infrastructure probably. And let me go and show you how electric vehicles can provide storage for wind. This is, I will. Just give me 1 minute, I'll be done, I promise. Thank you. Will Short's presentation from NREL. This is a projection from EIA forecast model with no new policy. And all I want you to focus on here is the total wind power. This is where wind is seen to go in by 2050. So this is as-is scenario. And this is a scenario if you introduce 50% of plug-in hybrid electric vehicles by 2020. This is the change that you could see in total wind power. That's it. I'm going to leave this conclusion slide up here and take any questions. Thank you.
Why don't we wait for questions until after the next speaker if there's time?
Okay.
I'd like to thank the Rice University for this invitation. I'm sure I wasn't here yesterday. I'm sure a lot of good things were said here about Rick Smalley. Many of you perhaps don't know, but in addition to my job as the executive director of the Institute for the Analysis of Global Security, which is an energy security think tank in Washington, I'm also the co-chair of the Set America Free Coalition. And Rick was a member of our coalition. The Set America Free Coalition is an umbrella organization of a number of think tanks in Washington, security, foreign policy groups, environmental groups, religious groups. All of them are in agreement that America's growing dependence on foreign oil is a major and urgent national security issue that needs to be addressed with everything that we have. And all of them agree on a blueprint for energy security that has been put forward a couple of years ago. And it is perhaps a very fitting opportunity to tell you that even though Rick is not with us today, today was a very important day for the Set America Free Coalition. A couple hours ago, two bills, bipartisan bills, were dropped on the floor of the Senate and the House, co-sponsored by a group of prominent Republican and Democratic senators as well as House members. And those two bills propose a major reduction of our oil consumption using some of the technologies that you are familiar with, particularly the increasing use of flexible fuel cars and plug-in hybrid cars. And this was something that Rick Smalley was, as you know, very enthusiastic about. I just recalled today when I heard Professor Carney speaking here about methanol, that our first meeting with Rick was when we tried to think with him what would be the most appropriate solutions to our oil dependence problem, and we started talking to him about the conversion of coal to methanol. And he was not familiar with this process, and he said, show me the paperwork, show me the evidence. So we went and piled up a lot of studies and information, and we sent it to him, and a couple of days later, he called and said, I'm having my coming to Jesus moment. And ever since then, he was a very good team member, and we will miss him. There are very good reasons why we need to care about oil dependence, which is growing. There are environmental reasons, but there are also national security reasons. We are facing today with high oil prices a situation of a transfer of wealth of historical proportions from the consuming countries to the producing countries. You all know what this money is doing overseas. We have very, very little liquidity mechanism in the market. There is no spare capacity. Terrorists understand this. They're hitting oil targets almost on a daily basis. They realize that this is a good way to hurt Western economy, drawing oil out of the market by blowing up facilities, not only in Iraq but elsewhere as well. Our supply lines are vulnerable. And we could face some hurdles down the road if we don't address the fact that our economy is not well insulated, because 97% of our transportation energy comes from petroleum. So if something wrong goes with petroleum, we don't have anything today to substitute for it, and that affects our way of life. And when we talk about oil dependence, it is important to remember that there has been a lot of progress in many other sectors of the economy. We have been able to reduce oil dependence in the utility sector, in the power sector, to almost zero. Only 2% of our electricity today is made from oil. That was not the case 30 years ago when it was almost a third. However, in the transportation sector, very little progress has been made. In fact, we're going backward on fuel efficiency. So this is the big bear to kill, and I think if we talk about oil dependence, we need to focus on the transportation sector and get massive efficiency gains there. Many skeptics say that we cannot accomplish a lot with what we have. I urge anybody all the skeptics to buy a plane ticket and go to Brazil and see what they've been able to do with domestic resources, just to give you a glimpse of what can be done if you stay the course for 20 or 25 years. Brazil, if you look at the blue line, that is the increase in fuel consumption in Brazil in the past 25 years, 80% increase. The red line shows you the level of dependence, from 80% dependence to about 10% today. So Brazil is effectively independent today. Some of it as a result of their ethanol program that brought about at least 25% of the liquid fuel in Brazil in the cars is sugar-based ethanol. Some of it is due to domestic oil production, offshore production of domestic oil. And no matter what the solution is, the fact of the matter is that if you stay the course of 25 years, you can really improve your situation dramatically. A lot of people are talking about CAFE and fuel efficiency standards. This shows you that there is a limit to how much we can gain if we do only CAFE. This is not a good enough solution. It's a very, very politically problematic approach. Hasn't accomplished that much. But even if we do everything we can do with increasing CAFE standard, the gap is very, very big, and we need something other than fuel efficiency standards, no matter what you think about them. If you are one of the people who are concerned about national security and the implications of our growing dependence on oil, then you probably have a different mindset to those people who say, well, we need to focus on moving around using less BTUs. Our problem when it comes to national security is not BTUs. It's oil and it's gasoline. So how do we stretch a gallon of gasoline and make it, how can we go the more miles using every gallon of gasoline? And this is what the approach that we are trying to promote is by fuel choice. And this is a country that offers us choice in every aspect of our lives. You go to Starbucks, you can choose from 30 types of coffee. You go to buy a carpet or a mattress, lots of choice. One thing we don't have choice is when it comes to transportation fuel. Everybody uses gasoline or diesel made from petroleum. So we want to try and change that. And the key to energy security is not necessarily to be independent, but to have sufficient choice so that if one system fails, we have something that can substitute for this system. What is it that we have a lot of? We have a lot of coal. We are the Saudi Arabia of coal. We have 25% of the world's coal reserves. We have some natural gas. We have nuclear, renewables. We have a lot of biomass. And if you look at the endowment of energy that we have in this country, other than petroleum, and we don't have a lot of petroleum, unfortunately, we can today produce alcohol fuels from both biomass or coal or natural gas, be it methanol or ethanol, but we can also produce electricity from the endowment that we have. And electricity is a transportation fuel. We don't tend to think about it as a transportation fuel. We don't think about it. We think about it as something that can light the room or heat our homes, but it is a fuel, and if we just know how to tap it and use it in existing vehicle technologies, we can make utilities providers of transportation fuel. Now, the reason we are excited about plug-in hybrid cars is because plug-in hybrid cars allow you to bring other sources of energy that have not been part of the transportation sector into the mix. So as I said, only 2% of our electricity is made from oil. The rest of the electricity is made from coal, domestic, nuclear, domestic, natural gas, mostly domestic, but increasingly imported, hydro, domestic. So most of the sources of electricity are domestic. So if you shift from petroleum to electricity, then you use more and more of the domestic resources, and you become less dependent on foreign sources of energy. So what are plug-in hybrid cars? Plug-in hybrid cars, you want to think about them as souped-up hybrids, the same Priuses that you see today on the road, but they can do something that a Prius does not allow you to do today. You can plug them and connect to the grid and draw electricity from an external charge. So when you drive a Prius, for example, you use gasoline from mile zero. A plug-in hybrid car has a battery that can store 20 or 30 or 40 miles of electric range, battery range, after which the combustion engine kicks in and it shifts seamlessly to liquid fuel. That essentially means that the first chunk of your daily driving will be on electricity. But unlike the pure electric cars that give you a limited range, with a plug-in hybrid, you enjoy both worlds. You have the ability to use electricity, but you don't have the range limitation that you face with an all-electric car. Now, some of you who live in Houston try to think about you trying to flee the city of Houston when a hurricane comes by, and after 50 or 80 or 100 miles, you get stuck on the highway looking for an extension cord. That is something that will be very difficult for most Americans to accept, the range limitation. And with plug-in hybrid cars, you don't have this kind of range limitation. You have a range limitation on the first chunk of your mileage, and then you can always use the kind of liquid fuels that we use today. Nighttime electricity, most people will charge the cars at night when utilities have a lot of spare capacity. And electricity is cheap during these hours. And with regards to performance, all the studies show that these cars have equal performance to regular cars. The interesting thing is that, as it was mentioned before, most Americans don't drive much. Most Americans drive approximately 20 to 30 miles a day. That means that they'll be using electricity most of the time. And we are becoming increasingly a plug-in society. You know, we come home, we plug in our cell phone, we plug in our computer, we plug in our laptop. so we'll plug in our car as well, and that is something that could be easily done. The benefit is huge. If you look at the efficiency gains here, let's take, for example, the red. The red is basically a plug-in that gives you a 20-mile range. A plug-in, a full-size SUV plug-in hybrid uses less gasoline than a regular compact sedan. So we're talking about a fuel efficiency of about, depending on how often you go beyond the battery range, but something like 100 miles per gallon of gasoline. There are significant environmental benefits because even on a well-to-wheel analysis, still plug-in hybrid cars emit much less CO2 than regular cars, almost half. And again, we're doing the well-to-wheel analysis based on the normal electricity generation, namely 50% coal, etc. We don't. We assume that we will stay within the same range of electricity sources. Let's go over the benefits. One of the main benefits is cost. If you use gasoline today at current prices, you pay today about 10 cents per mile. Every mile that you drive, it's about 10 cents. With electricity, it's about 3 cents, so significantly lower. We don't need infrastructure change. We all have electricity at home. So unlike other solutions that are floated out there, everybody has a washer, everybody has a dryer. You don't really need to invest that much in producing a new infrastructure, particularly when you compare this to hydrogen that requires a whole new set of infrastructure that costs you billions and billions of dollars. It allows us to shift to domestic fuel, which is very important. Interesting, the use of electricity also can change our market structure. Today, the transportation sector is basically a monopoly, if you think about it, because it's only dominated by oil companies. Plug-in hybrids or electric cars or use of electricity as a fuel brings new players into the market. Utilities. Utilities can enter the transportation sector. Utilities can generate liquid fuels. If you talk about conversion of coal to methanol, for example, or biomass to methanol, things that can be done in IGCC power plants, cogeneration of fuel and power in the same power plant. That's another way for utilities to enter the transportation sector. But it is very important in order to create the kind of competition that we need to see in the fuel market to bring new players into this market. And utilities could be naturals here, and they could really introduce the kind of competition that is very much needed. Plug-in hybrids, or electric cars, if you want, have a very interesting feature that they are basically the only cars that get cleaner as they get older, because our grid is becoming better, our electric generation capacity is getting cleaner, so the car is getting cleaner as it gets older. Those cars are beginning to move into the market, and in the past 2 years there have been significant developments. Daimler Chrysler has introduced the first set of 30 Sprinter vans, experimental, and they are already distributed around the country. There are people who are doing conversion of regular hybrids to plug-in hybrids using a kit that it's quite costly at the moment, but at least they are showing that this is something that is doable, and we have a couple of them that have shown a fuel efficiency of 100 and 150 miles per gallon of gasoline easily. So this is something that people are doing in individual capacity or small businesses, but I think that it sends the big auto manufacturers a message that if somebody can do it in a garage, you can also do it much cheaper way and much better if you're an automaker. Now, here is one of the most touchy issues here, and I think we need to really sort of think about this issue candidly and seriously. Our country, the Bush administration has made a commitment to hydrogen. You like it or not, this has been on the record. Billions of dollars of federal money have been invested in it. If you looked at the recently passed energy bill, it has a whole title dedicated to hydrogen. And I think that it is time to examine the benefits of hydrogen vis-a-vis the potential for plug-in hybrids. What could serve us quicker? What would make sense economically? And maybe it's time to reconsider, maybe it's time to change course, because I don't recall seeing an energy bill a whole title dedicated to plug-in hybrids. Now, there are significant benefits, significant advantages to plug-in hybrids over hydrogen fuel cell cars. As I said, they don't require change of infrastructure. They don't have the kind of safety issues involved with hydrogen. They are much more of a near-term technology. We don't have to wait decades before we see, like with fuel cells. And I think that the onus today on, when I talk to hydrogen proponents, I need to be convinced if there is merit to hydrogen. I need to be convinced. Why does it make sense to take electricity made from whatever makes sense, use it to split water, because that's what the whole hydrogen vision is. You make hydrogen from splitting water, not from coal or natural gas. You want to make it from renewables. Why does it make sense to take electricity, use it to split water, to create hydrogen, to put the hydrogen in a very costly fuel cell, in order to create electricity again, in order to power the car, when you can take the exact same electricity from the grid and power the car? This is what we are asking the hydrogen community to address. And until we get serious questions, serious answers about this, and serious explanations, why do we have to go through so many conversions and such a loss of efficiency? I think that there is no justification to continue to pour billions and billions of dollars into this program. The least we can do is extend the same courtesy to a competing technology that has much stronger feasibility of entering the market sooner rather than later. The bottom line is what we are proposing is a multi-fuel car. The vision that we have is a car that is very much like the Prius that you have today. It can be plugged in. It has access to the grid. But if you combine plug-in capability with the flex fuel capabilities, the combustion engine is a flex fuel engine that can run on gasoline, methanol, or ethanol, and that feature costs you about $150 per car, which is very, very little money. Then we're talking about a car that can do approximately 500 miles per gallon of gasoline. Per gallon of gasoline. Think about it. 500 miles per gallon of gasoline. And according to our calculations, if by 2025, for example, if all cars on the road are hybrids, and let's say that half of them are plug-in, because not everybody has the luxury of living in a house with a garage, let's say that half the cars are plug-in hybrids, and all of them are also flexible fuel cars, then we can have basically a massive reduction of our demand for oil in the transportation sector. Of course, there will be many other benefits other than environmental benefits. It will strengthen our national security. It will strengthen our economy. It will leave more money here rather than send it to people who don't like us. So this is the vision. All of the components are either already in the market or very close to commercialization. It's just a matter of leadership. It's just a matter of sort of plug-and-play approach. You can really use those technologies to complement each other. And I'm glad that I can address this forum in a day that we have seen shreds of leadership in Congress, and I hope that we can bring this to fruition quite quickly. Thank you.
Probably have time for one question if there are any.
So what are the batteries in the car?
Pardon?
What kind of batteries do you use?
Well, there are a number of approaches. Some people are more excited about lithium-ion. I don't know about that. There are some problems associated with lithium-ion. I think that nickel-metal batteries are the most likely, at least in the near term. But the jury is still out on which will be the most fitting battery for this kind of approach. There are pros and cons. The kind of batteries that are being used now by Daimler are nickel-metal hybrid batteries. However, the people that are doing the conversions of the Priuses are telling me that they think that they'll be able to do it with lithium-ion batteries.
Thank you all. Thanks to the speakers.